My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 565. In this lecture, I will continue my discussion on batch normalization. Let me recall my previous lecture, that is lecture number 564. In batch 1, I might see distribution like this. Just see this. In batch 1 distribution might be like this, in batch 2 distribution might be like this, in batch 3 distribution might be like this. As distribution change, they may not even normal, they may not even the Gaussian. As distribution changes, the neuron which is in layer 5, let me say neuron in layer 5 can go crazy. Neuron which is in layer 5 may go crazy because every time it is seeing different input or different distribution of input. Here problem is it is saying different inputs or different distribution of inputs. This problem is called, what is this problem? This problem is called what we discussed in last class, internal covariance. This problem is known as internal covariance shift. Sometimes people used to call it as covariate shift. Very simple. Internal means within the network. Here you are seeing the problem. Here internal means within the network you are seeing the problem, isn't it? Covariance is basically, what is my covariance? Covariance is basically, what is covariance? Generalization of variance. It is generalization of variance, isn't it? Covariance is generalization of variance to multiple variables. Multiple variables means what? It is generalization of variance to multiple variables. What is the meaning of multiple variables? I can say it means vector. Multiple variables means to vector instead of your input being a scalar, isn't it? If it's a vector, you can compute covariance, isn't it? What does it mean? If you have a vector, you can compute covariance. You can compute covariance. Here, variance is shifting. Here, what's happening in these diagrams? In this particular diagram, what's happening? Here, your variance is shifting. Mean is also shifting. Here, there is a covariance shift. This problem is called internal covariance shift or internal covariate shift. So the solution for this is also simple. Solution for this is my input x. Let me say this is my input x, and L1 is layer 1, layer 2, layer 3, layer 4, layer 5 output, and y cap. The idea is very simple. The idea is, suppose if I get batch 1 here, suppose if I get B1, B1 means batch 1 here followed by batch 2, B2 followed by batch 3. I can add a new layer here. Let me assume I am adding layer in between L4 and L5. Add a new layer. I will add a layer called batch normalization layer. What is that layer name? Batch normalization layer. It's a new layer. What I do in batch normalization layer is, whenever I get batch of inputs, yes, whenever I get a batch of inputs, as the name suggests, there is batch normalization layer, isn't it? Whenever I get batch of inputs, I normalize just that batch. That is important, isn't it? Whenever I get batch of inputs, what will I do? I normalize that batch. What happens? What is batch normalization? Take batch of inputs. Let me say b1 equal to x1 x2 so on x3 xk. I do simple data normalization on just this batch, not whole data set. For every batch I normalize it. When I do normalization on every batch, what happens? If I see one batch has this distribution of inputs, because I am normalizing it with mean 0, variance 1, isn't it? Because I am normalizing every batch that comes, the second batch also will have same distribution, and third batch, first batch, second batch, even third batch will also have same distribution, this mean 0 and variance 1, because I am explicitly normalizing each batch of inputs. Remember, not whole data, but just the batch. So batch normalization, you can think of it as addition layer, isn't it? You can think of that batch normalization as an addition layer that you are adding especially deep in the network. Batch normalization batch normalization works well deep in the network. If we add batch normalization, you will not have covariance shift problem. That is important. Yes, what is the use of batch normalization? You will not have covariance shift problem. We can train better. In the reference section, in the description section, I will give a link to research paper, the original research paper which discuss how there is one beautiful research paper which explains how batch normalization should be done. This is the original research paper from 2015. So let's assume I have mini batch capital B with m points x1 x2 so on xm. So here so I have my batch normalization layer in between layer 4 and layer 5. Suppose this is my batch normalization layer. It has some input and it has got some output. Suppose I have x1 x2 so on xm batch of inputs. How many inputs are there? M points. A batch normalization layer has two parameters. What are those parameters? Are called gamma and beta. And given an input, my batch normalization layer gets a batch of inputs. What are those inputs? As we are discussing, x1, x2, so on xm, isn't it? And what is this input to this batch normalization layer is input batch. What is my capital B here? My capital B is input batch, my capital B tilde is output batch, xi is input, xi tilde is output. You are sending xi to batch normalization layer and you are getting xi tilde, isn't it? Let's call this B tilde is batch, and that is output of batch normalization, isn't it? Batch normalization layer has got two parameters. What are those two parameters? Gamma and beta. Let's understand what it does. Instead of yi, here just if you observe, here I have yi. Just see this one. Here I have yi here. Here also I have yi, isn't it? There is a what will I do here now? Instead of yi here, I prefer to call it as xi tilde. Let me assume it as xi tilde. Instead of yi here, I call it as xi tilde. So given this batch, you are computing the mean of the batch. How can I calculate? Mu b. Let's simply call it as mini batch mean. It's a mini batch mean. Mu b equal to 1 by m into sigma I equal to 1 to m xi. That is mini batch mean. We are computing the variance of the batch. How can I calculate? Sigma b square equal to 1 by m, sigma I equal to 1 to m xi minus mu b whole square, isn't it? Computing the variance of the batch. And for every point xi, now you subtract the mean and divide by variance. Just see what am I doing? Xi minus mu b by under root of sigma b square plus epsilon, isn't it? What it means, for every point xi, now you subtract. What you are doing? You are subtract the mean. That's what I am doing for every point. For every point xi, just see, for every point xi, I am subtracting mean mu b, isn't it? And dividing by the variance, under root of sigma b variance, but you are adding a small value epsilon here, isn't it? You are adding a small value epsilon, because if variance is 0, then you don't want to have division by 0 error. Imagine if sigma b square is 0, epsilon is a small value. This is your xi cap. You have your xi cap is equal to xi minus mu b by under root of sigma b square plus epsilon. These three simple steps, what are these three simple steps? Mu b, calculating mini batch mean, sigma square b, mini batch variance, xi cap. These three steps are simple data normalization steps. So what batch normalization does, in addition to simple data normalization, take each of your xi cap, multiply them with just see what you are doing here. This is data normalization. What you are doing, your xi tilde equal to gamma into xi cap plus beta. In addition to simple data normalization, take each of your xi cap, multiply them with gamma, add them with beta. So this is called scaling. Multiplying is known as scaling and adding is known as shifting, isn't it? What batch normalization says is that I will learn my gamma and beta. Through back propagation. All these are differentiable. Which one is differentiable? Your mu b, sigma b square, xi tilde, all these are differentiable, which means batch normalization as an operation differentiable. Once if you have it as a differentiable thing, we can make it like an activation unit, which means you can add it as a layer. You are adding it as a layer with two parameters. You will learn your gamma and beta just like your weights. It could happen that your gamma may be 1, beta may be 0. I'm not saying this is always happens. If gamma equal to 1, comma, beta equal to 0, then what is your xi tilde? Your xi tilde equal to xi, which means you are simply doing data normalization. The only difference between batch normalization and the only difference between batch normalization and normalization is batch normalization has two parameters, isn't it? What are those two parameters? Two parameters which are gamma and beta, which are learned because you can learn it right, because whole batch normalization is differentiable, because computing a mean is differentiable, variance is differentiable, xi cap is differentiable. It is simple. It is simple addition and multiplication. Which one is simple addition? All these are differentiable, isn't it? It is differentiable. This is differentiable. This is simple addition. This is simple multiplication, isn't it? As long as something is differentiable, you can add it as a layer. You can have parameters to it, make it work through back propagation theory, isn't it? You make it work with back propagation. The only requirement for back propagation is you should be able to differentiate. So this is the core idea of batch normalization. Couple of major advantages with batch normalization. It helps you to have faster convergence. Reason is, for any neuron, inputs all are coming from same distribution every time. When such advantage occurs, you can afford to have larger learning rate. What is your rate update equation? Wkij nu equal to Wkij whole minus eta into dou L by dou Wkij. Because all your inputs are coming from same distribution, you can afford to have larger learning rate, which means you are going to converge faster. If eta is large, your new value slightly away from old value, which means you're converging faster. The second thing here is batch normalizer is also works as regularizer, isn't it? As a weak regularizer, not very strong regularizer, but you should use batch normalization in addition to dropouts. Please don't skip out dropouts. Dropouts do very good regularization. Batch normalization also has tendency to behave like regularizer. The most important idea here, it avoids internal covariance shift. When you avoid internal covariance shift, you can train deep neural networks. This is the core idea of batch normalization. This is a very interesting idea. I request all of you to go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.